All right. Okay, thank you everyone. Thanks for joining in today on a Monday morning. And again, I would like to start by thanking the MLIS team, as particularly Vedant, for inviting me today here to share some of our recent work with you. So, the point there looks like. So a little bit, very briefly, about myself before I start. So as you heard, I'm a senior lecturer working in computing science, where I co-lead a group called Social AI, and our focus basically is to understand human behavior, mostly in social settings with applications ranging from mental health care to social robotics. And we are interested in both analyzing and synthesizing behavior. Okay, so if anyone's interested in learning about our group's work, feel free to talk afterwards. Thanks. Probably I'll have to ask you to change slide. Okay, so back to the talk. So today we're going to talk about understanding human behavior using multimodal AI. So what exactly is human behavior? So the way I understand it, it refers to the ways that we act, interact, and experience the world. Now, you might think that's too broad, like that encompasses almost everything that we do every day, right? So let me unpack it a little bit so that I can be more specific what I mean by that. I have lots of animation, sorry, I have to do it myself. So let's imagine a scenario where maybe you're hiking on a mountain trail, and then you encounter a bear. Now that's maybe unlikely in Scotland, but maybe in Canada. So that's your stimulus. That's the event that will trigger some behavioral responses. So the first thing that is happening in your brain is multimodal sensing, which means your visual, your auditory senses are basically perceiving this information, and then your brain perceives this as a threat. Now, what happens next is that your brain will start forming some emotional state and also action tendencies. Action tendencies are not actions yet, so there's a precursor of actions, but emotional state will be fully formed at this point. And if you're anything like me, you'll be very, very scared, right? And what happens next, of course, is an action selection and execution. So your brain will choose one of these fight, flight, freeze mode. And if it chooses the flight mode, your preferred action is running away from the bear, of course. So this is what is of interest to me as a researcher. So I'm interested in the event, in the stimulus, interested in the emotional state and the physical behavior responses. This is it takes very short time from the event to be presented to the action that takes place. What happens afterwards is something like a more long-term process, which is out of scope for my research, but I know in psychology, neuroscience, people do very deep research understanding how our brain adapts and learns, updates our memory, and optimizes for such events for future cases. So to summarize, this is what I'm interested in for human behavior. I have some events, some stimuli, which can be seen or can be latent. For example, if it's an event that is an internal memory, then we will not be able to record it. We will not have access to the stimuli. Then you have some complex processes going on in the brain, perceptual and multi-level cognitive appraisals. Again, let's consider it mostly latent. We have not very good understanding of these processes. You might argue that I can measure some of the brain signals, but brain signals are not that easy. They're very noisy and a lot of problems there. And then I'm interested in the internal state and the physical actions, which I refer to as behavior in combination. And these states are observable through certain cues, behavioral cues. Internal state you cannot measure directly, so you need to rely on cues. Now, these behavioral cues are inherently multimodal. So here we are not inventing a multimodal problem. It is inherently a multimodal problem. So you, of course, have visual cues, which are very easy for us to understand, some body postures, gestures, facial expressions. We can also have verbal auditory cues when you're speaking to someone, you're interested in the content, but not only that, the intonation, the prosody, the laughter, all that comes with it. Now, these two are the overt channels, which means that this communication, these cues are produced so that another human can receive them and process them. We can also have covert behavioral cues, which are not seen easily, but you can measure them if you have right kind of devices. For example, the electrodermal activity or heart rate or pupil diameter. This can give you a sense of how stressed or aroused a person might be. So this is where the multimodality comes in, right? So as a computer scientist, as an engineer, this is how I view it. So you have some events, you want to get an understanding of human behavior, but some of these things you cannot measure directly. So what you can do is you can use lots of sensors that are available, whatever you can basically afford, whatever you can reliably use. And then you use these multimodal cues, capture them, process them, and use your AI systems to get an understanding of higher level behavioral aspects like intent and attitude, agreement, and so on. In my research, I'm particularly interested in using the theories and methodologies from speech and signal processing, computer vision, and deep learning to achieve these parts. Okay. Right? So before I give you some examples of our work, I just wanted to emphasize that this is a very hard problem. And of course, all these AI problems that we are currently solving are hard, are challenging, but understanding human behavior has some very unique challenges. So let me explain that. So if you talk about a computer vision standard problem like object detection, and if I tell you that the object within this green bounding box is a dog, I think everybody here will agree there is no subjectivity involved here. So we are dealing with an objective problem. However, this is not the case when you're dealing with internal states, for example. So if you have a facial expression like this, there's a lot of ambiguity, whether it's neutral, whether it's expressing happiness, sadness, who can tell? So there's this subjectivity involved in both perception, like how as a human I'm looking at it, and also in the production, because every human being is different and we are producing and expressing ourselves depending on the culture we come from, the experiences we had, and so on. So subjectivity and this huge variability in expressing and perceiving facial expressions and other visual and auditory cues, that's a huge problem. And another one is that of context. So context dependence. So human behavior is highly context dependent. If you do not know the context, it's likely that you will misunderstand what's going on. So here I have a quick visual example, because visual examples are easy to show on a slide. So what do you think is the internal state of this person if you just look at this face? Anger? Disgust? Okay, so maybe around that. So if I give you a little bit more visual context, this is what's going on, right? Of course, this tennis star is very, very easy to, if you've seen this before. So now with the context, you know that this is a case of sheer joy. It's a victorious moment. So that is the other problem. The observation has to be complete, which is very difficult to do in real world. So if you have incomplete observation, if you don't have the information about your context, then understanding human behavior, inferring the internal state, or even the actions can be very difficult. So This is where the multimodality can both help, and if you take it out because of their interdependence, it can make your problem very, very difficult to solve. Okay, so in my research, I am interested in understanding human behavior in different interaction scenarios. So of course, the highest level of interactivity that you can get is the human-human interactions. And in my research, I look at public speaking, how persuasive a speaker is when they're talking, and so on, and many other scenarios like disagreement and things like that. On the other hand, we have a lower level of interactivity where human is interacting with an object, such as media. I'm particularly interested in what happens when listening to music or watching a movie, what kind of emotion will be evoked as you interact with media. And in between, somewhere, we have the human-robot interactions where we are interacting with an embodied intelligent system. So that has a little bit higher interactivity than the human-human interaction, but lower than human media interaction. So this is where I'm going to focus a little bit today. I've been told it's only 20 minutes, so I'll be quick. And please let me know if I'm going over time. Okay, so I'm going to talk a little bit about our current work on understanding human-robot social interactions. So this is mostly the work of Tongfei, who's also present here. So if there's any difficult question that I cannot answer, I'm hoping Tongfei will be able to. All right, so what we have, since we're talking about social interactions, we are essentially interested in social robots. So if you look at most of the social robots that are available today, they're mostly designed for one-to-one scenarios, one-to-one interactions. And they're also reactive, by which I mean that they will start interacting only when the user starts interacting. So we want to change this paradigm to a proactive scenario where you have a case like this. So you have a social robot who's probably surrounded by different people. And what you want to do is you want the robot to know who is going to be the next potential user. And if we can do that, then the robot will be able to initiate an interaction instead of waiting for the user. So we believe that this will lead to better experience and natural interaction. Of course, that's something we need to still do the study, whether it actually can achieve that. However, in order to start doing that, we need to understand the whole view using a robot's perspective. So this is a very simple static view of a robot when in the lab, and basically has, whether you cannot see probably a lot of people here, but there are some people here and there in this view. There are other videos where you have more people. So the idea is that we want to, given all these people, we want to understand using their behavioral cues that who is interested in interacting with the robot. So this is how we formulate the task. So we want to just access a very early stage of interaction, just a few seconds, maybe 2-3 seconds, even less. And then we want to answer these 3 questions. Intent, which means who wants to interact with me as in the robot, so because it's from robot's perspective. Then we have attitude, so what kind of attitude the user has towards the robot, positive or negative. And then we have the action that will be forecasted, so future action, what might the person do to the robot. So you can see the first 2 are about internal states, and the last one is about action. This is what I was trying to say, that it's a joint prediction. I'm not separating the internal state from the action because we believe they are interconnected. And we often do not know which one happens first, which one influences the other. So this is what we want to kind of achieve. You have this kind of a very short video before the interaction even takes place. And in this case, of course, the person is approaching, so it's easy to see. And then we want to get this kind of inference where you have an intent and attitude and action predicted what's going to happen in future. So of course you use a data set for machine learning. We all know that. So we had to annotate this data set ourselves because this problem was new and there was no one working on this. So we had these data set where the videos were already there, but we did these annotations with different intent labels, attitude labels, and social actions like, hugging, handshaking, and so on. Okay, so again, now we're back to the paradigm of multimodal scenarios. You have multiple different cues. Here we are using body pose, distance as an implicit cue, hand gestures, facial expressions, head pose. Although we try to get gaze, but the faces are too small. In many cases, we could not get it to use very well. So we have the video stream here. It's not multi-sensory because all the cues are coming from the videos. And then you have these different cues extracted from it. Then you put it through your fusion, attention-based fusion module, and then you have a classification. In our case, we assumed the relationship among these three tasks to be hierarchical. They don't have to be. The true relationship is unknown, but we assume that, and now we are changing this to learn the relationship dynamically as well. So this gives you, some results. Of course, before that, I just want to say that these data sets did not have any audio. But if you had the audio, you could also do certain things. For example, who's talking to the robot, like whether we're talking to each other or to the robot, which is a very difficult problem from audio diarization point of view in the wild. You could also try to understand what is being said using ASR, automatic speech recognition. And then if you want to have a robot that could respond, of course, you are moving more towards agentic AI, and then you can use LLM and other agents to plan for the actions. So just some results. Many of you who publish in ML areas are very familiar with this kind of crowded tables. We put a lot of things crammed. So you don't need to look at all the numbers. The main point here is that our proposed model was very lightweight, which means that it's promising for deployment in the real world. Okay, so now more challenges coming in. So we did it in a static view robot. What if the robot starts moving, right? So you will have this kind of views where you don't even see the full human anymore. So this one was, we used a Spot, which is like the dog robot, if you have seen. So this data set was collected in ARC, and this data set has motion sensors as one of the modalities, and also the videos, the RGB videos, as one of your modalities. So we tried our model on this data set, and then we saw that it doesn't work very well. So that was one of the problems. You changed static to dynamic, you're having problems. And then you also ask questions, are the skeletons that are coming from the motion capture, are they enough? Do we need to use the RGB videos as well? Because you cannot see the skeletons fully, what sort of cues, how do you adapt to those kind of scenarios, which means you have missing points, you have corrupted modalities. How do we deal with that? And of course, if you keep adding more and more information, that means you're increasing the compute. So you have to do something about that so that you still have good inference speed, right? So our solution was to use a knowledge distillation framework where you have a large teacher model, and then you basically in inference time you'll be using a smaller teacher model. Now this is very common in model compression. The way we use it is slightly different, where we use the teacher model as a model that has access to all the modalities. And the teacher model has only one modality for its access. So this is the model in a nutshell. So we have a teacher model which can access all the cues, all the modalities that you have available. So it's very heavy, very accurate, but the student model can only access one modality so that it can be fast and still can give you some good results. And we also assumed scenarios where this input can be corrupted. So we use this model, train the student model after training the teacher model, as some of you, I'm sure, are familiar with knowledge distillation framework. so the results shows again these kind of tables. So what we see is the social C3D is the teacher model, which has the highest accuracy because it has access to all the modalities that are there. And the ego mobile one is where you're only using the student model for inference, which basically means that it doesn't have access to all the modalities. That's why it's lightweight, but in terms of performance, it's not as good. But still, it's better than if you had a same size of model trained from scratch. So we also looked at whether the knowledge distillation actually help. So what we found is that it does help in all cases. If you did not have, if you train the student model just by itself from scratch, it will not give you as good results and good performance, especially if you have corruption in your input. So we corrupted up to 60% of frames in the videos, and we saw that in case of these shaded ones are, I don't know if you see my mouse, but the shaded ones are the model's performance with knowledge distillation, and you can see that accuracy is still higher compared to no knowledge distillation. And we also looked at the contribution of different modalities and cues, and we found that at least in this task, each modality was important because whenever you take one out during the ablation, it will degrade your overall performance. So this is kind of a quick summary of our work. We are still working on this problem, and we are excited about the new results, but I'm not presenting them here in the interest of time. So let me summarize. What I wanted to convey today is that understanding human behavior is very challenging. You need a lot of modalities. It's inherently multimodal, essential. Yet multimodality will bring in new problems because you have many inputs to compute. They will be heterogeneous. They might not be in sync and may be difficult to fuse and so on. And I want to leave you with one question that we have been asking ourselves. So far we have been modeling this human-robot interactions by trying to mimic the human process of cognition. However, we do not know if that's the best process. We're just using it because that's what we know about. But probably it doesn't have to be that the robot should understand the human the same way the human understands the world. So if you have better ideas, we're happy to hear. Okay, so thanks very much. This was a joint work with my PhD student Tongfei and my colleague Matthew Cholet, who's also co-supervisor for Tongfei. If you have any questions. Do we have time for questions?
Dan's going to go around and...
All right.
If you have any questions, I'll be happy to